You're welcome.
Thanks very much. So thank you for that lovely introduction. Yeah, I've been looking forward to this for ages, and the conference has delivered exactly as much as I hoped, which was a lot. So thanks very much to the Matosin guys. You may know me from the internet as that Tarsier guy, or somebody who cycles a fair bit. You may be wondering how I manage being a Tarsier, but I just checked, and they've actually got really long legs. So I'm going to talk today about one of my favorite mathematical ideas, or two of my favorite ideas, in fact. One, my favorite idea in computer science education, and the other, one of my top N for small n favorite mathematical ideas. Probably number 2, if you ask me today. I can talk about what number 1 is in the pub later, or in the party later. So the first example is from Sicp, the Structure Interpretation of Computer Programs. So a little while ago, I did a port of most of the book into Clojure. And the example I'm going to go through first is from a paper in the 80s by a chap called Henderson. So it's like the Henderson Escher example. So we're going to talk about symmetry more generally, but this is kind of, if you like, my favorite thing from computer science education. So Henderson has the problem of how to describe Escher pictures, and in particular, rather than just describe them, he wants to sort of programmatically generate them. So he starts off with building a grammar. So you're going to get the 10-minute version of this introduction. So it's going to be quite quick. So he starts building up a grammar of pictures. So you say, if you draw George besides George, George is this stick man drawn here, and you've got functions that operate on the pictures. So if you flip George horizontally and then draw him beside himself, then you've got this way of combining and transforming pictures, which are just functions, right? So there's a function called flip horizontal, there's a function called beside, there's a picture called George, and we can sort of start talking about transformations of them. So if we've got a function called below and beside and flip horizontal, we can say, well, put below these two things, which is two things next to one another. So we start building up this grammar, if you like. We can say rotate George, which rotates him 90 degrees. And if you notice, the drawings are being scaled and always fill in the whole window. The window is an 800 by 800 square in this case. So we've got functions that transform pictures. Because we're inside Clojure, we can apply these functions, and we can create new functions that use them, higher order functions, if you like. Oh, they're not obviously higher order functions yet, actually. So we can say to rotate 90 degrees, we can do it twice and rotate 180 degrees. And then similarly for 270, we can create below if we've got beside and rotate. So we can sort of build new functions from old, which builds new pictures from old. So we then, if we get this recursive function that's recursing to the right, getting smaller and smaller here, unless n's 0, so we go n deep, and we can recurse. And this is going to give us our Escher picture in a moment. So the right split of George going 4 deep. It's actually 5 elements, because there's the 0 if 1 is the identity picture here. So this is the identity, right split. But because we recurse, because we call right split when we're inside right split, we have this nested picture. So a grammar's built up. You don't yet know what pictures are, but you can see because we've embedded it in Clojure, we can just call functions, make functions. So I haven't yet told you how to make pictures. Corner split, again, very similar. We recurse into the corner, and we split up, which is a bit like right split. So we're getting somewhere towards our Escher picture, which we wanted. The only thing I haven't told you is what George is, what is a picture in this. So we can do higher order procedures. So we can define a function called square of 4 that takes 4 other functions and draws a quartet of things. But each of the arguments is a function. So because we've embedded in Clojure again, we can use higher order functions. So I gave a talk at Euro Clojure. Around, because I use professionally DSLs like Puppet, and John mentioned earlier about this being in this constrained box of a toyish DSL without access to a full programming language being limiting. That's one of my sort of recurring frustrations and thoughts. So this idea that you should embed your DSL in another language I say other opinions are available. People like external DSLs, or like people want to be declarative or whatever. But I actually prefer embedded DSLs that are deeply embedded, because if you know Clojure, we can already talk about this. Even by embedding, you gain a lot. You have the whole of Clojure there. So another example, we don't know how to draw anything. So Quil, the drawing framework for Clojure, lets you draw lines. So if we can draw lines, then we can start doing some pictures. So we always say this, like, data is code, code is data. Very often that is almost used sort of trivially. It's like the code is S expressions or lists are a data structure in our language, so we can do macros and things like this. This example here is actually more like the procedure is going to be the data. So the actual function itself is going to be the data, which is this is for me the biggest aha moment in Sicp, which is actually sort of full of aha moments. So this idea that a picture is a function that takes a frame as an argument and takes the responsibility of drawing itself. So the picture itself is a function. So what you might have thought of as data is actually a procedure. So there's another aha in Sicp in a similar vein. So they only use const cells for the whole of the book as the only data structure. So you have const, char, and coulda for creating and taking elements of these pairs. And then they implement the pairs as functions. So for the entire book, you only have one way of making data structures. And then at some point, they kind of pull the rug out from under you and make everything out of functions. So const, char, and coulda, your only way of making data structures are implemented in terms of functions. I've got an old blog post about it called Creating Something from Nothing Twice, I think it's called. Sorry, that was an ad lib. I didn't plan to say that. So take a frame, draw a picture in it. That's the responsibility of the picture, which is a function. Yeah. So the frames are just described as an origin and then a vector offset. And then our first picture just draws the outside of the frame. So it draws a line. So if we've got frame 1 and frame 2, we can call frame painter on it because that's just a picture. Picture takes a frame and draws itself. So the frame painter meets our interface. So then what does the draw function do? So when you say draw a picture, it actually takes the picture, which is a function, and passes it the whole window, which is the frame that's the width and height of the thing I'm drawing. So I hope that's clear so far. If you can do that, then we can transform the pictures inside. So flip and rotate are defined in terms of a transform picture function that in this 10-minute presentation of this idea, I can't really go into, but there's a slightly longer version of this talk from Clojure D where I try and do it. I think the treatment in Sicp Distill is actually quite good, and you get to very quickly sort of build these pictures in Quil, which I'll show you in a moment. So yeah, if you can define above in terms of rotate and besides. So again, because they're functions, you can use them the way you normally would as arguments and return values of functions. So I've kind of localized it. So I usually take a sort of attractive local monument or something. So Quil also lets you draw pictures. So we've said that Quil has the concept of a picture, but we've got the concept of a picture, which is a function that takes a frame and draws itself in it. So we can have an image painter, Miko, an image painter that just loads this picture of Miko. And you say, draw Miko in frame 1, or you say, draw Miko in frame 2. So if that meets our interface, doesn't it? So if this image painter, now we can go and we can do things with Miko that he may or may not approve of. Oh yeah, the image painter, I'm not actually very good at, you'll see in a minute, I'm not actually very good at 2D or matrix geometry. Mathematics was my degree, but I haven't done very much like graphics and stuff, so I'm actually not great at doing the manipulations. But this is a suitable matrix to do the correct transformation. That I'd like to say I just worked it out, but I was bashing, trying different stuff for probably too long. I shouldn't even admit that. So we can say we create a function called square limit, which you can pass some picture. This is obviously an Escher tile, and you hand it the angel's picture, and it draws the square limit of it. Square limit is the name of the painting. Oops, sorry, I've gone too far. So as part of the Sicp distilled thing, you have a framework that you can answer in, and you can start drawing things. So obviously, having a REPL is quite nice. I think the original one you was using like an SVG lib, or so it would generate images, but it took a while. So it's quite nice that computing's kind of moved on, and we can sort of interactively build up these things. So we have this like combine for function, which takes those images, flips them, rotates them, etc., and puts them on top of one another. And as a thanks to our host, so sort of take the Matosin logo, flip it round, and I think the square limit of Matosin. That's a sentence probably no one's ever said. There you go. So we've got this kind of like grammar and for describing them and stuff. So how am I for time? Perfect. Halfway through. Awesome. I'm halfway through the slides. So that's a very brief presentation. I think it's one of the most wonderful aha moments I've ever had in computer science education. So I would say like this idea of representing the pictures as procedures, and then suddenly a whole swathe of stuff that you can do, especially in a language that permits higher order functions, is suddenly all there. And we haven't built a parser or a description of Escher or anything. The embedding allows us to do that. And of course, you can see the structure is recursive. So when you look at the pictures, the idea is Escher's drawn to a certain point, but the idea is that you can express that forever to infinity kind of thing. So I rather like that. So the title of this is The Symmetries of Things, so a book by John Conway and co-authors. I'm afraid I don't know them so well. But John Conway is an incredibly prolific mathematician, a hero of mine, if you're allowed to have heroes. So he's also the Conway that did Conway's Game of Life. My number one mathematical idea is probably combinatorial game theory, which he also co-discovered. And probably my third is the surreal numbers, which he co-discovered as well. So, and the structure of the book's quite interesting. Very often we have this idea that mathematics is like an edifice of things that you build, and as you sort of layer on, you sort of build in on things you've previously done. But this book kind of flips the order a little. So it says, we start with a problem, we introduce tools, then we were presented with a second problem. Well, do the tools work? So we have to prove that there's a solid mathematical foundation behind them. That involves making more tools, which then need a justification. So the book has this wonderful flow of showing you something, and then saying, well, why does that work? Oh, it's because of this other thing. But is that valid? So you kind of have this, like, it punts off into the future, the description. So you get the result you want quite early in the book, but then a whole bunch of things has been postponed. So as a sort of like, I'll be punting things off to the book, obviously, because I'm only here for 10 minutes. So I've probably spoke too much. Can't do anything about that now, I suppose. There's two main kinds of symmetry in the plane. If you've got a finite shape, then it must fix a point. So we call this Nfold kaleidoscopic. You might have seen mirror symmetry, but the book says kaleidoscopic. It's Nfold kaleidoscopic symmetry fixing a point. And n can be for any of the integers, right? There can be as many mirror lines as you want, and you just divide up the image, and it has to be symmetrical within that. You've got Nfold gyrational, you might say rotational, symmetry, fixing a point again. That's the flag of the Isle of Man and a suitable car wheel. So there are two main examples of finite, symmetrical 2D things. If you have infinite ones, so there's a whole thing of freeze patterns. So the freeze pattern, you imagine you've got a roller, like here, you can actually get Escher cookie cutters, which I'm quite pleased about. So you can actually, you can see from the top picture that that's sort of equivalent to the surface of a cylinder, isn't it? So if you draw something on the cylinder, you can repeat that and go on forever. So that's a kind of like a translational symmetry, but just in one dimension, yeah? But then there's things like this, which sort of permit, or rather invite, a different description. So you can see where the noses of the blue lizards meet. There's a kind of three-way mirror symmetry, right? And similarly, other points are meeting in what looks to be a three-way symmetry. So sort of taking the simplest one, so this is an infinite plane. We're now talking about filling the whole plane. This sort of stereotypical like 70s wallpaper is kind of like, it exhibits several lines of symmetry, and if you follow them all through, then you can see that actually, if this is reflection of this, this is reflection of this, then it's actually, the whole picture is induced by the single triangle. So if you reflected every edge of the triangle, you would have the whole plane filled. And if you look at the angle, so one is 2 mirror lines meeting, so it looks like a right angle, I think. Yeah, so 2 mirror lines meeting, one's got 3 mirror lines meeting, and one's got 6 mirror lines meeting. So that's a unique description. We order it, we say 6, 3, 2, rather than any of the permutations, we just decrease. So that's a standard. So yeah, that would be like 6, 3, 2, gyrational symmetry, kaleidoscopic symmetry. So you say star 6, 3, 2, and it's colored in red. But this has obviously got something else going on. There is a mirror symmetry, you can see, but there's also a rotational symmetry, and it's in the gaps. So I don't know if you can see my pointer. I should have increased the size of the pointer. There's an image that zooms it in a second. You see, in the gaps, that's not a rotation. That's not shit. That's not a mirror symmetry. That's not a kaleidoscopic point. It's a gyroscopic point. It's a rotational symmetry there. So this would be 3 star 3. Does that make sense? There's a 3-fold gyroscopic and a 3-fold kaleidoscopic symmetry. And there they are depicted. And again, that is now induced by the triangle. The whole plane is filled by taking copies of that. And here is the Magic Theorem. Again, the proof is punted into the future when you go out and purchase the book at fine bookstores. So the theorem states that any solution to the plane tiling has a cost of 2. So the symbol 2 has cost of 1/2. So we could have 4 of them. There's a plane symmetry. And similarly, we've got a whole bunch of things. So this infinity is worth 1, and then and then 2 other infinities. The total would be 2. And you see here we've got 222 is the one I just said, wasn't it? 222 is there. So far you understand all of these. These are triangles. This is a triangle of mirrors. This is a triangle. Sorry, this is a triangle of rotational points. And the 4, 4 means there's 2 distinct ways of doing the 4-fold rotation. And I haven't said what these crosses and dots mean. I'm probably, how am I for time? 2 minutes, okay. So there's 2 other concepts. One is a so-called wonder ring, which there's only one of, and there's only one because that symbol costs $2. So we must know that that's another tiling of the plane, and there it is. It's translational symmetry only. So there's no mirrors and there's no gyrational symmetry in it. It's just this single translation, a so-called wonder ring, which you draw with an O. So Conway's very imaginative in the language. These are called miraculous or miracles. So they're 2 points that are the same that somehow don't draw in between them, doesn't cross a mirror line. So this has mirrors, do you see, which is the star, the single star. But there's also this miraculous crossing that doesn't cross a mirror. If you're intrigued, you can read the book. I definitely recommend it. So because I'm not so good at 2D geometry, I haven't found a good way of expressing these. So I've got to the point where I can draw and reflect within. But I can kind of brute force it and reflect without the bound-in hexagon in this case. But I haven't found a nice way of expressing it, so I've toyed with a few ideas. I've got one that works for points but not images. So if anyone's curious about helping me build this up, that would be awesome. Maybe you're as bright as Henderson. I'm certainly not. I think that's it. Oh yeah, I would recommend this book. The Symmetries of Things is very accessible at the beginning. At some point you need group theory. People are often asking me for recommendations for maths books. Not often. Not as often as I'd like. Here's a recommendation for a maths book, I should say. So this book is a little bit idiosyncratic. It kind of projects through what would be like 8 or 10 undergrad courses, but it's a unified view on it. So if you've never studied complex numbers or whatever, it's an abstract algebra book, but it takes you through introductions to the quaternions and things like this, things that you would get to quite late in a maths course. But it kind of the fact that the chap has a unified view to try and get you to the point where you can, and symmetry is informing, and it's the connections between algebra and geometry. So very much a sort of standalone book that will take you like a really, really good sampling of an undergrad maths course, and say a unified vision around it. So if you just bought one book, this would be a good book. Well, as well as the other books, the Symmetries of Things as well, and other Conway ones. Sorry, I'm waffling anyway. Some links here for Henderson's paper, etc. Geom Lab I found very interesting, which is an intro to functional programming for kids based on some of these ideas. That was actually what informed I've done an implementation of Geom Lab in Clojure, which I really prefer embedding in Clojure to a toy language. That was kind of my point in that talk. And now, questions? Oh, thanks for your indulgence.
Thank you, Tommy. So any questions? What I love about Tommy's talks, that they are pretty much every time useless for your day jobs.
It is a perverse satisfaction of mine, yeah. I must say.
I love it. So, there, Joseph, to the right. Tommy, please.
So thank you for that talk. That was great. So I'm also a big fan of these embedded DSLs and using functions as data. This is awesome, yes. But one thing that you can, so one of the pitfalls there is that you have functions, then if you don't do things in the right order, so to say, you may evaluate the same function many times, and you get into inefficiencies. And in particular, I'm looking at these Escher-like pictures where you have lots and lots of pictures going almost into infinity. So can you tell me a little bit about how you handle that and if it's been a problem for you?
I've got a funny answer, which is before I started this, that used to say George 10. I lowered it to 7 because it takes ages. So the answer is I actually don't solve it. This is not a performance implementation, especially with the drawing of the lines. So it hasn't drawn yet, I don't think. So if I go back to, you can see how long this takes. If I go back to this draws fairly quickly, I think. Oh, see, it hasn't even finished. Yeah, so there's that. But if I want the George to depth 10 instead, I mean, I don't know if I can recur from that. If you looked at the code, I actually just name the function again. So I'm probably, but I don't know if, I can't remember if it's in a tail position. But I'm definitely, it's definitely not quick. So I don't solve the quickness problem in this case. In general, procedural abstraction, I think, has a value. You're right, there's potentially a performance penalty. But
I mean, there are ways to solve this, but often it requires a bit more of the programmer, like introducing sharing and stuff like that. And I mean, it gets a little bit in the way of, especially here when you want to draw beautiful pictures from beautiful descriptions. So, but there are ways around it.
I forget what I think it's SKI combinators or something. One of the early sort of precursors to Haskell used to compile to those combinators, and then they had to get a fast way of doing it. So it might be that you punt it off to the compiler, and like if people are doing this procedural abstraction all the time, then you assume the compiler or the runtime should permit fast execution of that.
So there are several ways of doing this, and maybe we should take it offline. But real quick is that you can try and rediscover the sharing that was already there. But then you've introduced, so you already introduced the exponential growth there. So that's not a good problem in general. The other one is to require some kind of sharing up front that the programmer provides, and yeah. You just have to have some syntax for it in your DSL.
Yeah.
Anyway, thanks.
Cool.
Yeah. One more? Ah, yeah, there.
Okay, thanks. This made me think immediately about the book Gödel, Escher, Bach. Maybe somebody else have been trying to read it through as well. So what about doing the same stuff for music? Have you been thinking of that? Maybe taking overtone and combining?
Oh, it would be, I would defer to Chris Ford if you've not seen any of his talks. Chris Ford has absolutely bossed it over the last few years of some stunning talks about music. Chris and I have riffed a fair bit about this idea of DSLs and whether they should be embedded, etc., and sort of escape hatches and things like this. I often talk about, you know, like the fact that Terraform permits the JSON description is actually gives you an escape hatch. They could say you could generate their code, but the fact that they permit kind of deliberately the JSON interrupt format is an idea that I often riff off with Chris, but I would just defer to Chris, any of his talks.
Okay, thanks. Have to check it out.
All right.